Hello, this is the last lecture on renal physiology and renal function test. This is the first one. We will talk on this lecture about two functions, secretion function and reabsorption function, and renal blood flow through the nephron. Physiology shows that there are many metabolic functions, and chemical interaction can be determined through the laboratory tests for renal function. We have three renal functions: glomerular filtration test, and we call clearance test; tuber reabsorption test, and as we call concentration test; tuber secretion and renal blood flow test. Tubular reabsorption test, as we say, concentration test. Firstly, measurement of GFR is not a useful indication at early renal disease because reabsorption ability is the first function affected in renal disease. So reabsorption ability can determine the early renal disease. Tubular reabsorption can be determined by specific gravity, osmolarity, and free water clearance. The first one, determination of specific gravity. Concentration test, as we say, is tubular reabsorption, are determining the ability of tubules to reabsorb the essential salts and water, which not selected filtrated by glomerulus. Ultrafiltration tubules has a specific gravity 1.010. Thus, after reabsorption, the final urine product should be higher or more concentrated. But when we make more urine samples as a routine test, we see specific gravity higher than this number and lower than this number, but no renal disease. So the urine concentration is determined by the body state of hydration. The normal kidney will reabsorb only the amount of water necessary to keep the body water. The two scientists, Fishberg and Musenthal, make another method to determine the concentration test. This method has been used to reduce water deprivation before measuring specific gravity. The patient were deprived of fluids for 24 hours period to measure specific gravity and making comparison of the volume and specific gravity for day and night samples. To evaluate concentration ability, and this test not used now because the information provided by specific gravity measurement is useful as a screening test, but quantitative measurement of renal concentrating ability is done by osmometry. We have an example to study the effect of hydration on renal concentration. We have two patients, patient A and patient B, where patient A drink 1 glass of water and patient B drink 4 glasses of water. When the water passes through the glomerulus, the kidney filtrates the same amount of the solute and same amount of water, 120 milli per minute water and 300 milligram solute in the both. When the reabsorption done, the patient A reabsorbing 119 milliwater and 100 milligram solute, and the patient B reabsorbing 110 milliwater and 100 milligram solute. So the both reabsorb the same amount of solute, but they are different in the amount of water which are absorbed. So the urine in patient A has 1 milliwater and 200 milligram solute, and the patient B has 10 milliwater and 200 milligram solute. So the two patients have the same amount of solute in urine, but they different in the water volume. This difference make different specific gravity. So the specific gravity in patient A is 1.015, and the patient B specific gravity is 1.005, and this depended on the substance, absolute concentration, the urine, and the body hydration. The persons with normal concentrating ability should have specific gravity of 1.025 when deprived of fluid for 16 hours, and overnight water deprivation make urine osmolarity is 200 milliosm or above. This indicates the normal concentrating ability. Osmolarity. Specific gravity depends on the number and the density of particles present in the solution, but osmolarity is affected only by the number of the particles. When determining renal concentration ability, the important substance should look for is the small molecules. Sodium, molecular weight 23, chloride molecular weight 35.5, urea molecular weight 60. The urea affects more to the specific gravity than the other sodium and chloride because of size of molecule. Because all these three of molecules, sodium, chloride, and urea, have the same effect equally to the osmolarity of the specimen, so more accuracy to renal concentration ability can be obtained by measuring osmolarity. Clinical significance. Major clinical uses for osmolarity will be to determine the renal concentrating ability, monitoring renal disease, monitoring fluid electrolyte therapy, doing differential diagnosis for hypernatremia or hypernatremia, estimation of renal response to ADH. Normal serum osmolarity between 275 to 300, normal urine osmolarity between 50 to 1400. This because more factors influenced on it like fluid intake and exercise. The more accurate is by determining the ratio of urine to serum osmolarity. Urine under normal condition, the ratio of urine to serum osmolarity should be 1 to 1. Under controlled fluid intake, the ratio in urine to serum osmolarity should be 3 to 1. The ratio of urine to serum osmolarity with procedures such as controlled fluid intake and injection of ADH is used to differentiate if the diabetes insipidus is caused by decreasing ADH production or inability of renal tubule response of ADH. By controlled fluid intake, we must reach ratio 3 to 1. If you can reach this ratio by injection of ADH, that means the amount of ADH is low. And if we can't reach this ratio 3 to 1 by injection ADH, that means no receptors on the collecting duct functional for ADH. And now after that we know what's the reason of diabetes insipidus cause. Is it by inability to produce adequate ADH or no receptor for ADH on the tubular function? Free water clearance. The ratio of urine to serum osmolarity can be more useful by performing the analysis using the water deprivation time urine specimen collecting the free water clearance. Free water clearance, we say this equation. Example, using urine osmolarity is 600 and urine volume is 2 ml per minute. Plasma osmolarity is 300 milliliters. As we say, the equation. So we will discuss what in this equation. Calculation of the osmolar clearance indicate How much water must be cleared each minute to produce urine with the same osmolarity as the plasma? The ultrafiltrate contains the same osmolarity to the plasma, so the osmotic difference in the urine are the result of renal concentration and dilution mechanism. By comparing the osmolar clearance with the actual urine volume excreted per minute, it can be determined if the water being excreted is more or less than amount needed to maintain the osmolarity and the same to the filtrate. Free water clearance of -2 indicates that less than the necessary amount of water is being excreted, but possible state of dehydration. If water clearance is 0, no concentration or dilution takes place. If water clearance is 2 pi plus, excess water has been excreted. So, calculation of free water clearance is used to determine the ability of kidney to respond to the state of body hydration. Tubular secretion and renal blood flow. Major tubular secretion of non-filtrated substance is related with renal blood flow through the nephron, so it must be measured by the substance which secreted rather than filtrated. But impaired or inadequate tubular secretory ability and decrease of renal flow of blood cause abnormal result. So the test most commonly associated with tubular secretion, the renal blood flow is p-aminohypuric acid pH or phenolsulfonophthalate PSP. Standardization and interpretation of PSP results are difficult because of interference by medication, evaluated waste product in patient serum, obtaining several urine specimens different time. So PSP test is not currently performed. PAH test, p-aminohypuric acid, measurement or measuring the amount of blood flowing through the kidney by using substance that's completely removed from the blood or plasma each time is contact with the functional urinary tissue, and the principle is like the clearance test for glomerular filtration. pH is good substance to measure renal blood flow because non-toxic, loosely bound to plasma protein, completely removed when the blood passes through the peritubular capillaries, except for a small amount of pH doesn't come into contact with the functional renal tissue. The plasma pH is secreted by proximal convoluted tubule, so the volume following the plasma through the kidney determined by amount of pH excreted in the urine. Based on the normal hematocrit reading, normal renal blood flow range 600 to 700 ml per minute, and renal blood flow about 1200 ml per minute. The standard clearance formula, as we say, the actual measurement is renal plasma flow, not renal blood flow, because the pH contained only in the plasma. About 8% approximately of renal blood flow not contact with the functional renal tissue. Amount of pH infused must be monitored carefully to ensure accurate result. Use radioactive hypochlorite can determine the renal blood flow by measuring the plasma disappearance of single radioactive injection, and at the same time provide visualization of blood flow through the kidney. Nitrogen acidity and urinary ammonia. Ability of kidney produce an acid urine depend on tubular secretion of hydrogen ion and ammonia by distal convoluted tubule. The normal person excretes approximately 7 ml equivalent per day of acid in form hydrogen ion, phosphoric acid, and ammonia. There are variations in urine acidity where lowest pH found at night alkaline appears shortly after a postprandial. Inability to produce acid urine in metabolic acidosis is called renal tubular acidosis. This condition results from impaired tubular secretion of hydrogen ions associated with proximal convoluted tubules, defect in ammonia secretion associated with distal convoluted tubules, measurement of urine pH, acidity, and urinary ammonia used to determine the defective function. By measuring the amount of free hydrogen ion, titratable acidity, and the total acidity of the specimen, so the ammonium concentration can be calculated as a difference between the titratable acidity and the total acidity.